Hello and welcome to this video. In this video we're going to be looking at the topic of errors. So when we make measurements in physics, we can never be 100% certain of what measurement we've made. Okay, there are always going to be errors. There's always what we call uncertainty on the measurements that we've made, and this is a really important thing that we have to abide by. Although most people will actually hate doing the whole error analysis and making sure all of your values are correct and all of that kind of stuff, it is really important, because if we take an expected value and we find so our expected value, let's just go with an expected value of g to be 9.81. This is what we expect it to be. If we then find that we have a experiment set up that measures the value of g, and we measure that it's actually 15.2, right? How do we know if we're right and this is wrong, or if we've just got we've done something wrong, an experiment has gone wrong? Okay, and we can say that if we were to say this is like plus or minus 10 meters per second squared, I have to keep our units and everything. This means that within this range, so this plus or minus means that if I can have a range of uncertainty on this measurement. So either it's 15.2, or it can be anything from 5.2 up to 25.2, which means we include 9.81. And so this is still a valid measurement because our uncertainty is massive. And this is why we will tend to do this error analysis, just to make sure that we could repeat all of these experiments and still get consistent results. So even if we repeated this experiment 1,000 times, we should always get the same result if this number is right. Now, the type of data we get, we can usually say we'll never just take one value. Okay, so we never take one value. Okay, we always take multiple values. If we just try and measure one value, then basically the scientific community isn't going to accept that you measured it once. It needs to be repeatable and reproducible. So you need to make sure that you could actually make this exact same measurement again, and to prove that you can make it again, you just make it again. And so what we'll get is actually going to be a set of data. So we'll get a bunch of things. Let's say, for an example, that I'm just going to measure the length of a rope, and I measure it once and I see that it was 23 centimeters, and then I'm going to measure it again and see that it was actually 24 centimeters, and then another person comes along and measures it and says that it's actually 23 centimeters, and then another person says that's 22.5 centimeters, and so on. Okay, we can keep getting more people to use the same instruments to measure this length of rope, and they could all get different values that are roughly around the same. And so how would we get a single value from this? Well, we take the mean. Okay, our mean, as we should know, should be the sum of all of the values divided by the sum of how many there are. Okay, so the total frequency. So in this case, if we wanted to work out the mean, we would do 23 plus 23 plus 24 plus 22.5, all divided by 4. And that would tell us what the average length of this rope is. But again, this can't be an accurate value. So if we calculate that value, it gives us 23.125 centimeters. And we know from what we've been looking at, we've only actually been able to measure to the highest degree of accuracy of 0.5 centimeter. Okay, and we're assuming this is going to be with a ruler. We'll look at errors with specific instruments in a bit, but we can't get to this possible degree of accuracy, and so this can't be the actual value. But there is some uncertainty on this value. That means that the actual value that the length is going to be in there somewhere. Okay, and the way we can calculate that length or that uncertainty in its simplest way is to just take a half of whatever the range is, and then put that either side. Okay, so if we say the range is actually, we take our biggest value minus the smallest value, so our biggest value is 24 minus 22.5, we get an overall length or overall range of 1.5, and then if we half that, we get 0.75. So actually in this case here, we could say that the length of this rope is actually going to be 23 I would just stick to 13 here, plus or minus 0.75 centimeters. And this is how we would write our final result. Okay, so we know we have some value, but we're not completely certain that that is the correct length, and so we have to put some uncertainty on that measurement. Okay, so coming from here then, how do these errors form? We have different types of errors that we can look at, and they will form dependent on the situation. So the first one, and the one we have least control over, is called random error. Okay, so random error is literally you'll just make some measurements, and then in one of your measurements you'll have some form of random error. It's not due to any fault of the apparatus or any fault of the experiment. It's just a random error that occurs because something random has happened. Okay, so this is just an occurrence or a random occurrence which causes a measurement to become anomalous. There we go. Okay. What do I mean by anomalous? Well, an anomaly is just a piece of data that doesn't fit with the rest of it. So, for example, if we were measuring this length of wire again, and I got 23 centimeters, I got 24 centimeters, and then someone come along and said it was 12 centimeters, I know this is an anomaly because it's nowhere near what these are saying, and so this has to be wrong. And what we usually do with anomalies is just ignore them, because we're saying that this amount of error is way too high. We know that's not going to be an acceptable result, and so we just get rid of those results. So random error is the first thing, and this is something we can't control. Something that we can control is something called zero error. Now this is an error in the equipment that you have. Okay, so with things like rulers and that kind of stuff, you're not going to get zero error because your zero is have been painted on or drawn onto whatever this is. But if you think about scales, for example, if you've ever looked at a pair of digital scales, there'll always be a reset button. Okay, and the reset button basically sets this to be 0. If you stand on the scale and then you press the reset button while you're on the scale, it makes your weight its new 0 point. Okay, if you then step off the scale, you'll get a negative value. Okay, and so where you're actually measuring no mass on top of this scale, you're having some negative value. And this is a zero error. It's where your point on your apparatus where the 0 should be, i.e. so the 0 should be where no mass is measured. What the 0 is actually changed, because the 0 point is the mass of the person who was stood on that scale. So this doesn't just happen in scales, it can also happen in things called micrometers or also vernier calipers, where if you set the instrument to be 0 and you read that it isn't actually 0 when there's nothing inside the instrument, then you have a 0 error. Now the way to handle 0 error is just to say, so let's for example say the weight that you're or the mass that you're measuring was minus 25 kilograms, and then you put something onto it, and then what you actually read is let's go with 20 kilograms. We know that the total mass that, so this is minus 25 here, but this is 20 kilograms. We know the total mass that you've actually measured is going to be 45 kilograms. Okay, so what you're going to do to get rid of your zero error is you minus it from the original result. So you'd have 20 minus 25, and that would give you the 45 kilograms. Okay, so to solve zero error, you always minus the zero error from your result. Now this works as well. So if you were to say that you're originally measuring 25 and then you positive 25 when there's nothing on the scale, and then you end up measuring 50 when something is on the scale, your measurement is 50, you minus the zero error, which is 25, and you can tell that you've measured something of 25 kilograms. Okay, this idea of minusing the zero error from the result will always work, even if it's not working with scales. So this is how we deal with zero error. Now the last type of error that we're going to look at is called parallax error. This sounds really fancy, but it's not actually as fancy as you think. This word parallax just refers to the position of your eye as you're reading an instrument. Let's, for example, say you wanted to measure the length of the rope, and now what you're looking at is your ruler is here, and you can have all of your measurements for your ruler like this, and this will go on, but your rope is over here. Okay, and you're trying to measure the length of that. You're going to have to kind of guess, where does this actually meet the line? And by guessing that, you get some parallax error. Okay, so this is when the viewer has a distorted view of the apparatus. Okay, so this doesn't have to just be when we're reading things off of a length, but we know what to do in this situation. That would be easy. We just have to take this rope and put it closer to the ruler. And if we put it closer, almost lying it directly on top of the ruler, you can then know that that's directly there, and that's going to be directly there. And now you can accurately measure what the length of that ruler is. It can also happen if we're reading something where we might have to see a line. So for example, if you wanted to read the volume of a liquid in a container or something like that, if you're, let's say this is the container and the volume of the liquid comes up to this point here, and it has some measurement on it, but then you're going to see it from this angle, looking from down here, you're actually going to see that it reaches it at this lower angle. So what we have to do here is correct the position and make sure you're looking at things like this at eye level. Okay, so view at eye level. Okay, and this is how we deal with parallax error. So you just have to make sure that how you're measuring it is acceptable, essentially. They aren't too big of a deal, so these shouldn't make huge problems in your values, but by decreasing the amount of errors that you get, you're going to find that you'll get more accurate values, and then it'll be more impressive and you'll have more fun in lab. Thank you for watching.